Okay, good morning, everyone. Welcome to the calculus class. And before I start today's class, let me explain regarding the midterm one more time. I got a couple of students' email, and I don't know why they are sending emails actually. Okay, so we have the exam on Wednesday. Okay, so we have the midterm on 22nd April. Okay, Wednesday. And this is offline, in-person exam. I repeated this announcement of several times, and I still got email asking the date of the exam or the format, or asking is it offline or online exam or something. Okay, so let me explain. Okay, the last time. Okay, so this is the offline in-person exam, and you must, as I announced on the syllabus, so you need to come Hana Science Hall, oops, room B214 in the basement, not second floor. Okay, please come to the basement of the building, and please find room B214, okay, in Hana Science Hall. So that's the place you will take the exam. Now, the calculator, if you want to bring with you, fine. But not the cell phone apps, cell phone or tablet apps. So if you have only cell phone app, that's not allowed. Only the actual calculator. Okay, so the actual calculator is allowed, not the cell phone apps or tablet apps. Those are not allowed. And no electric device such as laptop, cell phones, tablets. Those are not allowed. Okay. So please, if you use any of these devices, that will be considered as a cheating, and I need to report the school. Okay, I need to follow the rules, and I need to be fair with all the students. So no electric devices are allowed except your calculator. And regarding the cheat sheet, yes, you can bring it with you. It's A4 size, A4 size paper, but one side only, and that must be handwritten. So if your paper includes any image or some reduced image of the textbook or slide, that will be confiscated. You cannot use them. Okay. Okay, the ordinary calculator will be the accepted. Okay, A4 size or smaller, it will be fine. Okay, so A4 size paper or smaller will be fine. And just one side, if you have some formula on both sides, it'll be confiscated as well. And it must be, as I said, handwritten. Okay. So this is the information. I showed some sample problems the other day. I mentioned the coverage. Actually, the coverage was announced on the first day. So if you missed any of these, please watch the video lecture on the YouTube. Okay, I have those lectures on the YouTube, and you can also find the syllabus describing this information. So please check this syllabus, or if you are not certain, please watch the video lecture again. And okay, so the covers, so the midterm covers chapter 1 up to chapter 5. Okay, so those were mentioned multiple times, I guess. Now I believe now it should be clear. Okay, if you have any other questions, let me know now. Okay, then let me start the next part of the lecture. Okay, so we are going, so the exam, the midterm covers chapters 1 through 5. Okay, and the only sections I considered during the in the class will be covered. So if I skip certain section, you can skip those sections as well. So this is the information regarding the exam, regarding the midterm. Okay. Okay. Mm, about 9 or 10 problems will be given. About those are not fixed yet, but probably 9, 10 problems will be given. Anyway, so even though I considered the section 1 in chapter 6, that those will be considered will be in the final exam, not midterm. Okay? So what did we consider in section 1 in chapter 6? We considered two curves, and then we want to measure the area of the region bounded by two curves. So sometimes we are given two graphs like this. So we have the graph of y equals f of x and y equals to g of x. And they have some intersection. So say they have some intersections at 2 points, say A and B. Then we can find certain area, a certain reason bounded by the graphs of two functions and this intersection. Or sometimes, even though they do not have the intersections, I can consider two vertical lines at x equals to A and x equals to B. Then these two vertical lines and the graphs, we can find certain, we can define certain region, and we want to measure the area of this region. Okay, so sometimes we have such functions, but in some situation we are given, say, x equals to f of y, and I have another function, say x equals to g of y, and in this case y is an independent variable. So in type 1, so in these two cases, the x is an independent variable, but sometimes we have the situation where y is an independent variable, and in that case we have two functions, x equals gy and x equals to f of y, and say two horizontal line at y equals to c and y equals to d. Then we can define certain region bounded by the graphs of these two functions and two horizontal lines, and we want to measure the area bounded by these two. So in these cases, so in this section we considered those. So so if I have two functions, f of x, the y equals f of x, I'm asking to find the derivative of this. To differentiate and choose one of these four, which is the derivative of given y. Okay, so I have this two functions, y equals to f of x and y equals to g of x, and if I have this region S bounded by these two graphs and certain vertical lines at x equals to A and x equals to B, okay, so in that case, so if you have a situation as in figure 3, then you need to integrate the graph above minus the graph below, and then you integrate that difference from A to B. Okay, so in this figure, the one above is the graph of y equals to f of x, and one is below is the graph of y equals to g of x. So f of x minus gx will be integrated from A to B. So that will give you the area. Okay. So if I have two functions, e to the x and y equals to x, then your task, as I said, is to find the function which is above. And one simple way to identify this is to draw the graph of these two functions. So when I draw the graph of e to the x, we have this. And if I draw the graph of y equals to x, you get this one. And if I consider two vertical lines at 0 and 1, then these two vertical lines and two graphs will define this shaded region. And if you want to find the area of that region, you need to integrate e to the x, which is above, minus the x, which is below, and then you need to integrate this function from 0 to 1. So that will give you the area of the shaded region here. So that is your task. Now, sometimes, sometimes two functions may oscillate. And so, I mean, on certain interval, say f of x is above gx. And in another interval, gx is greater than f of x, so that the graph of gx is above the graph of f of x. Now, if I just integrate the f of x minus the g of x, then that integral will be sometimes positive on some interval and will be negative on other intervals. So that if you just integrate f of x minus gx, then there will be certain cancellations. Okay, so if you want to, so depending on the problem, if you want to find the area between two curves, then you always integrate the absolute value of f of x minus gx from a to b. So the absolute value is a must. You must put the difference between these two inside the absolute value sign. Okay, and then you integrate that in absolute value of f minus g from a to b. Previously, in the previous case, when one function is just above the other one on the whole interval, then this absolute value sign is meaningless when you measure f of x minus gx. So f minus g does not change the sign, but it is always positive. Then you integrate that f minus g from a to b. But if that sign of f minus g changes during the on the interval, depending on the subintervals, then you must put that difference function inside the absolute value. In other words, you need to integrate the absolute value of f minus g from a to b. So that was what I considered when we have two functions in x. In other words, when x is an independent variable. But sometimes we are given two functions where y is an independent variable. Then instead of, so there is no graph above or below. But in this case, we have one graph which is to the right of the other, or we have one graph which is to the is on the to the left of the other one. So when you have such functions, then you integrate f of y minus gy from c to d when f of y is always to the right of gy, as in figure 10. Then you need to integrate f of y minus gy from c to d. Okay, so depending on the situation, sometimes you need to consider the integration of f of x minus gx from, I say, a to b, or f of y minus gy must be integrated if you are given two functions in y variable. So please practice this. Okay, now today we are going to consider the volumes. So we will first define what a volume is, and then we will continue. So suppose that I have a simple cylinder as in figure 1. Okay, so the top and bottom have the same shapes and the same area. Okay, so B1 and B2, these two regions, top and bottom regions, they have the same areas. And suppose that this cylinder has height h. Okay, so this line segment height, whose length is h, is perpendicular to B1 or B2. Okay, and suppose that suppose that the area of B1 and B2 are both A. So the area of B1 or B2 is A. So A represents the area of this bottom or top region. And suppose that the height is h, then the volume of the cylinder will be the area of the base, which is a, times the height h. So the volume of the cylinder will be defined by the area of the base a times the height h. Now, in particular, if the base is a circle with radius r, then we know that the area of the circle is pi r squared. So if you have a cylinder with a circle, I mean, if the base is a circle, as in B, then the circular cylinder has the bottom of circular cylinder has area of pi r squared. So if you multiply the height h, then the volume of such a circular cylinder will be pi r squared times h. If the base is a rectangle with length L and width W, then the area of this base is the area of the rectangle, which is given by length times width. So the area in that case is L times W. So if you multiply H to this area, then you get the volume of such rectangular cylinder or rectangular box. So the point is, whatever the area of the base, if you multiply height, you get the volume. The problem is this. The problem becomes complicated when you want to measure the volume of a solid, and if that solid is not a cylinder. Okay, so if you have a solid S that is not a cylinder, in that case, what we can do is this: we first cut this cylinder, we cut this solid into small pieces, and each piece is approximated by some cylinder. So each piece is approximated by a cylinder. And then we estimate the volume of this solid by adding the volumes of the cylinders. And when these pieces are considered, okay, when I cut this solid into pieces, if I increase the number of pieces, so if the number of pieces is increased, then even though this cylinder is an approximation to a piece, the difference between a cylinder and this small piece from the solid will be negligible in some situation. I mean, in some limit case. Okay, so if I increase the number of pieces, okay, I mean if I introduce infinitely many pieces, then the errors, the difference between the pieces and the approximating steadiness will be negligible, and eventually you will obtain the volume of a solid. So, and there will be several ways to cut this solid into pieces. And the first approach we are going to consider is to consider, we start by intersecting S with a plane and then obtain a plane region that is called a crosscut. I mean, let me show you this with some figure. So suppose that I have a solid as in figure 2, the blue one. And let so if I have such a solid in space, so I have a solid in three-dimensional space, and suppose that I have a plane which is plane which is perpendicular to x-axis and passing through the point X, which means I have a solid in space and I have a big knife. Okay, so with my big knife I cross. Okay, I cut this solid into two pieces at point X. Okay, and when I cut this solid, okay, my knife goes, okay, perpendicular to the x-axis. Okay, and at that point there will be a cross cut of this, and the area of the cross-sectional area will be denoted by A of x. So A of x represents the area of the cross section of S when I cut this solid, okay, with my knife at point X. So A of x represents the area of this cross sectional area, the cross cut. Then let me assume that this is solid, okay? When I put this solid in space, the smallest value in x is A, and the solid reaches up to, say, B. And if I introduce many points, say x naught, x1, x2, up to xn or x7, and let me assume that x naught represents the initial point A, and x7 represents the ending point B. So if I cut this solid into pieces at those points. So if I cut this my solid at those points, okay, then so if I cut this, so here is my x naught, and when I cut this at x1, then it will have a certain cross-sectional area. When I cut this at x2, you will have another cross-sectional area, and so on. So if I cut this interval, if I cut this solid at x1, x2 up to x6, then you have some pieces. You have 7 pieces, right? Now, if I approximate each piece, okay, so so if I cut this into 7 pieces, then I have this. So let me. So when I cut this at xi minus 1 and xi. Actually, so I have this piece is not a cylinder in general. Okay, this is so when I cut at xi minus 1 and xi, then the piece obtained by these two cutting is not a cylinder. So what I want to do is this. Between xi minus 1 and xi, I will choose an arbitrary point. And let me use xi star to denote that point. Okay. Now at that point, I will evaluate. So at that point, I will measure the cross-sectional area. I mean, at this point, I will measure the area of the cross-sectional crosscut. Okay. And then I will consider a cylinder. I will consider a cylinder with AXI star as the crosscut area. I mean the area of top and bottom of the cylinder, and then I will use this width between xi and xi minus 1. So I will use the delta x to denote this length, and I will consider a cylinder with this delta x as the height. So I have this cylinder, and the area of this top and bottom is the cross sectional area at xi star. And the height of the cylinder will be delta x. So I will consider such a cylinder. And even though there is some discrepancy between the actual piece and the solid, I want to approximate the volume of this piece by the volume of this cylinder. So if I cut this solid into 7 pieces, I will introduce these 7 cylinders. So the first one is has the, I mean, for the first cylinder, the area of top and bottom will be the actually the cross-sectional area at x1 star. So we will have x1 star, and we will evaluate the cross-sectional area at x1 star, and then multiply delta x to get the volume of the cylinder. In a similar way, between x1 and x2 star, you will choose an arbitrary point, and I will call that point by x2 star. So x2 star, I will evaluate the cross-sectional area, multiply delta x, and that is the volume of the second cylinder. So I will repeat this procedure for all 7 cylinders. So if I add the volume of these 7 cylinders, then that will be an approximation of the actual volume of the solid on the left. Okay. So so the volume of each piece is approximated by the volume of a cylinder. So the volume of the whole solid will be approximated by the sum of the volumes of the cylinders. Okay, so at this point, so if the number n is small, such as 5, 7, then the discrepancy between the actual volume V and the sum on the right will be large. But as you can imagine, when I increase the number of pieces, mathematically, if I increase the value n, so as n goes to infinity, okay, in other words, as the number of pieces increases to infinity, the discrepancy between the actual volume and the sum of the volumes of the cylinders will decrease to zero. So the volume can be defined, volume of a solid in mathematics is defined by the limit of the sum of the volumes of the cylinders. Okay, so if such a volume, such a limit exists, then we call that limit value as the volume of a solid. Okay, since this is a Riemann sum, when I introduced the Riemann sum, I told you that when a Riemann sum exists, okay, then I will call that limit as the integral of the integrand a of x dx. So here a of x denotes the ax denotes the cross-sectional area at point x. So if you integrate that cross-sectional area, okay, from a to b, then that will be the limit of the Riemann sum, and that will be called the volume of a solid. Okay, so you may forget about this procedure of the derivation of a volume, but you must remember that the volume of a solid is the integral of the cross-sectional area. So a of x is the representing the cross-sectional area. So if you integrate the cross-sectional area, you get the volume. Okay. So as I said, the a of x is the representing the cross-sectional area. If you integrate that cross-sectional area from a to b, you get the volume. So if you are asked to find the volume of certain three-dimensional solid, the first approach we consider, okay, we are going to consider a couple of approaches, and the first approach is to integrate the cross-sectional area. So in case of, for example, if I have a circular cylinder, then that means I have this three-dimensional solid in space, and if I consider the cross section at point A, cross sectional area at point X, then if the cross sectional area is a constant, say A, then the volume of this cross sectional, the circular cylinder, will be the integral of this constant from A to B. Okay. Now that is consistent with our previous formula, because the length between B minus A just represents the h, the height of a cylinder. So h is b minus a. So the integral of a just represents the volume of this circular cylinder. But this formula can go beyond this simple situation. So as long as you can measure the area of the cross section, then you can find the volume of a three-dimensional solid. So let us consider the following example 1. So suppose that we have a sphere of radius r. Okay, and so let me put this sphere so that in this in three-dimensional deep space, so that the center of the sphere, okay, matches is at the center. I mean at the origin. Then when I consider any point x, when I consider the crosscut, the cross-sectional region will be a circular region. So all I need is the radius of this circular region. So I need to estimate the y value, okay, the y coordinate of this point. Okay. So given this point P, then it has the coordinate of x and y. Okay, and since this point is on the sphere, by definition of the sphere, the distance between this piece of x and the origin will be the radius r. Then by the Pythagorean theorem, please note that this triangle is a Pythagorean a right triangle. So this triangle will satisfy the Pythagorean theorem, which means the x squared plus y squared will be the hypotenuse squared, which is r squared. So here x and r are given. So y squared will be r squared minus x squared. So y will be plus or minus square root of r squared minus x squared. Since so so if I assume that y is positive, I mean, because you might consider this point as your px here, but let me just choose px so that it is located in the first quadrant. So if I define p sub x by the point on the first quadrant, then y will be positive. So that y will be square root of r squared minus x squared. So that is y. Then what is the cross-sectional area? The radius squared times the pi. So the cross-sectional area is pi times radius, which is y in this case, y squared. So which is pi times r squared minus x squared. So that is the cross-sectional area. Okay. So the volume of the solid is the integral of this a of x from a to b. So there are two ways. So you can integrate pi times r squared minus x squared dx from minus r to r. Or since when you look at this figure 4, okay, the left hand side and right hand side, okay, with respect to the y-axis, they are symmetric, right? So instead of this integral, you can integrate r squared minus x squared times pi from 0 to r, and you can double it. Or mathematically speaking, this integrand pi times r squared minus x squared is an even function. So the integration of the even function from minus r to r will be 2 times the integral of the same integrand from 0 to r. So the volume is the integration of the cross-sectional area, which is this function. But as I said, this pi times r squared minus x squared is an even function. So you can integrate this integrand from 0 to r, and then you can multiply 2. Okay. Then the antiderivative of r squared will be r squared times x, and the integrand of x squared will be x cubed over 3. So by the fundamental theorem of calculus, we can evaluate the difference of this antiderivative at two endpoints, right? So if you do this calculation, you get this. So that will be the volume of the sphere, and that is consistent with the result you learn in, I'm not sure, middle school days, high school days. Okay, that is consistent with what you learn in geometry class. Okay. Mm, so I already explained this one. Okay, so the idea was this: given this sphere with radius, say r, if I cut this sphere into, say, 5 pieces, as in figure A, then there will be some discrepancy, okay, between the volume of a solid and the actual volume of each piece, right? But that discrepancies will decrease if I introduce the more pieces. I mean, if I introduce, say, 10 pieces, then the discrepancy between the actual volume and the volume of a solid will be much smaller than that from 5 pieces. And if I increase the number of the pieces to, say, 20, then the error, the discrepancy between the actual volume and the volume of a piece will be smaller and smaller. So if I let the number of pieces go to infinity, okay, then the error will decrease to 0. So that's what happens in this example. Anyway, so in this first approach, I just cut this solid, okay, into many pieces. And when I cut this, you will consider certain the the intersection between a plane and a solid, and we assume that this plane is orthogonal to the x-axis. So that is the first approach we considered. Now, now I want to consider the second approach, some different approach. So if we revolve a region about a line, I mean, if I have a certain region, and if I revolve this about this line, what do I get? This upper part will generate some three-dimensional shape is obtained. And the lower part will introduce somewhat smaller. So the revolution of the lower part will generate some somewhat smaller solid is obtained, right? So I have a figure like this. So if I have a region like this, then and then if I revolve this about certain line, then then this lower part will generate certain curve or sphere, and this this portion will generate somewhat. Okay, we have some. So we have somewhat smaller solid is generated, right? And so this region will generate certain portion corresponding to the okay. So this portion will generate something like this. So that okay. So do you understand what I'm saying? So the blue line generated this outer sphere, and this red curve will generate the inner sphere, okay, and the area will the region in between will generate this three-dimensional solid in space. Okay, so if I have such cylinder, I mean such solid, okay, then how can I generate, how can I get the volume? Okay, so if I can find the cross-sectional area, then I can integrate it, right? I can integrate the cross-sectional area from A to B. So that is simple. Then, so the task is how to find the area of the cross-sectional cross-section. So if I have such solid in figure 10, when I cut this at point X, then you get a piece, okay, which is similar to a piece such as a pineapple piece. So the cross section is the okay, so the blue line will generate the outer sphere, outer surface. Okay, so at point X, if I consider the cross cut, you get this blue circle. If I consider, okay, and but this red point will generate a smaller circle. Okay, so so if at point X, then the red curve will give you, say, R1, then the red circle has radius R1. And the blue point, if the distance between the x-axis and this blue curve is, say, R2, then this is R2. The radius of the blue one is R2. So the cross-sectional area is the area of this pineapple-shaped region. And the area of the pineapple-shaped region is the area of the blue circle minus the area of the red circle. The area of the blue circle is pi r2 squared. The area of the red circle is pi r1 squared. So the difference between these two will be the area of this pineapple-shaped region. So that will be the cross-sectional area when the solid in figure 10 is generated, is obtained by revolving certain region like this about some line. So let us consider some example. Suppose that I have okay, so I guess something, okay, I made, so this slide is a typo. There is a typo. So find the volume of the solid obtained by rotating the region, okay, defined by x equals to square root of y and x equals to y. So given these two lines will generate some region, okay? So if I devolve the region about y-axis, I'm sorry, about x equals to -1 line, okay? Do you understand? So I'm revolving this region in purple. So that is the region bounded by, defined by these two functions, x equals to square root of y and x equals to y, right? So given x equals to square root of y, we have some curve like this. And then if I consider x equals to y, I have a straight line. So I have this region, okay? Now I want to consider a vertical line at -1. X equals to -1 line is considered. And then this shaded region is revolved about y-axis, about this line, x equals to -1. Okay, so you get some revolution about x equals to -1, then you get certain three-dimensional solid. And in this problem, in this example, I want to find the volume of that solid, okay? So all I need is the cross-sectional area. Since y is given in this problem as an independent variable, when I consider the cross-sectional area, I'm considering the horizontal plane. Okay, so if I consider a cross-sectional area at y, okay, then then so here the outer curve. So when I say outer in this case is the graph of x equals to f of x equals to square root of y. So this outer function, the outer curve will generate the outer circle. And the revolution of x equals to y line, okay, the red line, the revolution of that line will generate the inner circle. Okay. So the revolution of x equals to square root of y will generate the outer circle. The revolution of this x equals to y will generate an inner circle. Then what is the radius of the outer circle? The radius in this case is the distance between the curve and the axis of revolution. So if I consider any point y, the distance between the axis of revolution, x equals to -1, and the outer curve, x equals to square root of y, what is the distance between these two? I need to measure the distance between x point on this curve and -1. So x is square root of y. So the outer radius is the x value in x coordinate in y variable. So square root of y minus the x value of the axis of revolution, -1. So that is the outer radius. Okay. Then what is the inner radius? The distance between the x coordinate of, so here, x equals to square root of y. That's the case of the outer curve. In case of the inner curve, the x coordinate is just y. So the inner radius is the distance between the x equals to y curve, the red curve, and the axis of revolution, the x -1. So y minus 1, which is y plus 1, will be the inner radius. And what was the formula then? Pi times the outer radius squared minus pi times inner radius squared will must be integrated, right? And in y variable, and what will be the integral domain, the limit of the integration? Y value must go from 0 up to this value. What is this value in y? So I need to find the intersection, the y coordinate of the intersection point. The intersection is given when y coordinates are the same. Okay. And that happens when Y is 0 or 1. Y is 0 represents this the lower intersection, and upper intersection corresponds to the value 1. So the integration must be performed for bit from 0 to 1. So if you integrated this from 0 to 1, that will give you the volume of the three-dimensional solid. So, oops, just, oops, sorry, this is plus 1, sorry. So this is 1. So if you integrate this, from 0 to 1, we can find the volume of the solid. So let me go back to this example. This is difficult, right? But so if I consider the reason defined by x equals to square root of y and x equals to y. So in the exam, I will give you just these two functions, okay? I won't give the figure. So you need to check, okay, given two functions, and if you consider the revolution, you need to check which function will define the outer radius and which function defines the inner radius. So, so note, given two functions, x equals to f of y and x equals to g of y, or sometimes you have two functions in x variable. You need to check which function defines the outer radius and which function defines the inner radius. And when I say outer, that means in case of a function in y variable, then when I say outer, okay, the one on the right, when I have two functions in x variables, then when I say the outer, that means no, might be confusing. It's because that when I so let me correct this. So when I say outer, that means between two functions, okay? You need to find the one function which is farther from the axis of revolution. So in this figure, the axis of revolution is x equals to -1. This is the axis of revolution. Now, between two curves, the red one and the blue one is farther, right? from the axis of revolution than the red one. So the blue curve will generate the outer radius, and the red one will generate the inner radius. In this figure, the outer radius comes from the blue curve because the blue curve is farther from the axis of revolution than the red one. Red one is closer to the axis of revolution. So red one will define the inner radius and the blue one will define the outer radius. We now find the volumes of solids that are not solid of revolution but whose cross sections have areas that are readily computable. So let us consider some example. So figure 12 shows a solid with a circular base of radius 1 and the parallel cross sections perpendicular to the base are equilateral triangles. Okay, and find the volume of this solid. So, okay, so when I cut this solid perpendicular to the base, I mean, then you get a equilateral triangle. If I have such solid, then I want to find the volume. Okay, then what will be the cross-sectional area in this case? So let's take the case like this one. Let's take the circle to be the x squared plus y squared equals to 1, the unit circle, and the solid its base and the typical cross section at a distance x from the origin are shown in this figure. Okay, so the base is a circle, the circle x equals to y, x squared plus y squared is 1. So that's what happens on the xy plane. So when I consider the xy plane, you get this circle in blue in B. So this blue curve is considered, blue circle is considered. Now in space, in three-dimensional space, okay, I have a solid, and if I consider the cross section, then cross section region will be the triangle as in figure A, equilateral triangle. Okay. Then what will be the area of this triangle? We need height and the base of this triangle. Okay. And since this cross section is this equilateral triangle, okay, and if the coordinate of B is x and y, x, y, and the z coordinate is 0, then the B has, I'm sorry, not B, coordinate of A is x, y, 0, and coordinate of B is, say, x, negative y, and 0. Mm, no. X, y, 0. That is correct. X, y, 0. And let me assume the coordinate of A is x, negative y, and 0. Then, then B has the coordinate of x, y, and 0. Z coordinate is 0, so on the xy plane, the point B has the coordinate of x and y. So that means height is y, and this is a unit circle with radius 1. So radius measures the distance between 0 and the origin and point B. So that distance is 1. So if I consider this, oops, oh, okay, time's up. So let me continue after the break. Okay, so let us take a 15-minute break, and then let me continue this, okay, after the break. Okay, um, so let us take the break. Okay, you can. Oh, where is it? Okay, you can leave the classroom and let me continue after the break.